Chemical equilibrium. In order for a system to be at equilibrium, you have to realize that chemical reactions are reversible. What this means is not only can the forward reaction take place, but also the reverse. Not only can reactants form products, but under the right conditions, products can reform reactants. And if they're doing so at the same rate, this is defined as chemical equilibrium. In this video, we're going to learn how to solve introductory equilibrium problems. That is, when a system is at equilibrium when the rate of the forward equals the rate of the reverse. How do you identify that a system is at equilibrium and that you're not doing stoichiometric calculations? If you'll look here at the double arrow in the chemical equation, this is indicative of a system that has the ability to reach equilibrium. If you're doing a stoichiometric type calculation, you would have only a single arrow. Now, the easiest type problem that we can solve for dealing with equilibrium is when they say, here we have a system, a chemical reaction that is already at equilibrium. If you have a system that is at equilibrium, you should be able to calculate what is called an equilibrium constant, a numerical value that gives you information about this system. To calculate this equilibrium constant, which we symbolize with Kc, you have to be able to write what is called a mass action expression. A mass action expression is nothing more than the ratio of the concentration of the products, in this case the SO3, over the concentration of the reactants, the SO2 and the O2. And to represent concentrations, we're going to do so in molarity. If you recall, this is moles of solute per liter of solution, so we're going to be dealing with moles per liter to represent things correctly in what is called a mass action. So the first thing we need to do is write our mass action. And our mass action is down here at the bottom, and I'm showing the SO3 product. I'm showing it in brackets, which stands for molarity, moles per liter. And notice that the coefficient that balances the equation in the mass action becomes an exponent. This is the one thing that students usually forget whenever they're solving equilibrium problems. So make sure that you're aware that whatever this exponent is, whatever this coefficient is, it becomes the exponent in the mass action. So products always go on top, reactants always go on bottom. So here we have the SO2, it's on bottom. Notice the coefficient becomes the exponent here, the 2. The oxygen is on the bottom as well. Reactants are always on the bottom, so products over reactants. And if you have all equilibrium values, which was stated in this problem, and very seldom a problem is going to be this easy. This is the simplest type of equilibrium problem you can have. All you have to do now is simply plug in your values into this equilibrium. So we're going to plug the 0.15 in here. We're going to plug the 0.3 in here, and the 0.75 here. And when we do so, we'll be able to calculate a numerical value for the equilibrium expression. Now, just because something is equilibrium doesn't mean you have the same amount of reactants and products. Equilibrium can favor one side or the other. If your K value is less than 1, which it is here, it means equilibrium ever so slightly favors the reactant side. So equilibrium doesn't mean you have equal amounts. It simply means that the rate of the forward equals the rate of the reverse. Equilibrium can favor one side or the other, and that is what this numerical value provides you with. Another type problem, this is also one of your easier problems. We'll call this a level 1 problem. And notice here all equilibrium conditions are provided again. And all we have to do is essentially plug these values into our mass action. Now, to do so, we have to write products over reactants. Notice all the coefficients in this case are an understood 1. We'll put them here just for emphasis. And we can plug our values into our mass action. Now, you may see that I've been setting up a chart each time that talks about initial conditions, which none were given here. We're given a system at equilibrium, and here are all the equilibrium values. And when they didn't give us the unknown, of course we can represent that as an unknown algebraically with an x. But if initial conditions were ever given, we could actually talk about what changes they had to go through to get to equilibrium when the rate of the forward equals the rate of the reverse. But in this case, all we have to do is plug in what we know about our equilibrium conditions into our mass action. And it's always products over reactants. That's not going to change. And now what we'll be able to do is simply solve for the unknown concentration at equilibrium. Once again, this is one of the easier type equilibrium problems. And the reason this is easier is because equilibrium conditions are provided. They didn't start us off with the initial conditions, and we had to go through the changes of where the rate of the forward would eventually equal the rate of the reverse. The next type problem I'd like to talk about is perhaps a level 2 problem.